Working?
Yep.
All right, guys, let's get started. So, still on orbital parameters, and we'll talk about ground tracks. So, one thing that is happening tonight, I just used my ISS spotter app that you can download. You can also look online. So, at 7:59 p.m. tonight in Gainesville, not very high, 33 degrees above the horizon, but you should be able to see if, not with these clouds, but if it clears up, you should be able to see the ISS going by. I'm sure that many of you have seen that dot flying around. You can spot it from almost anywhere if you plan ahead, and it's at night. I've seen it once with the space shuttle when it was still flying. That was about to dock, so we could see the big bright point moving, and then a smaller one just following. That was pretty cool. So I'm telling you this because today we'll talk about ground tracks, and using the ground track, I'll do everything mostly in MATLAB. I'll show you how we can forecast that this is actually happening tonight, more or less at 8 p.m., which is pretty cool, I think. Everything done in MATLAB. You can then redo it in SDK. But before we do that, let's see a few other examples. Well, actually see some examples of why this orbital parameters business is actually useful. And the first one, so we said A, E, I, big omega, little omega, and theta are a way to tell where the spacecraft is. These first five, in the ideal case of R double dot equals minus mu over R cubed R, are constant in time. While this is an alternative to time, it tells you where that point is on the orbit. But as we'll see later on here, there will be other accelerations that we call disturbance accelerations, for which none of this is really constant anymore. They may oscillate, they may drift in time, they may do strange stuff. That is usually a perturbation, something we do not like, but nature sometimes can be exploited to do something that we do like. So the fact that some of these orbital parameters do not remain constant, but they change in a certain way, may be useful. And we'll see an example right away without going into the math details, because again, we haven't done anything about additional forces. We'll get there. But I want to show you right away why we even care about talking about these angles and same major axis and eccentricity. So the example we really want to look at is Sun synchronous orbits. So let's, Sun synchronous means what it means. You are synchronized with the sun. You want your satellite to possibly be illuminated by the sun all the time for the obvious reason of maybe powering the system, having solar panels always active, or maybe you have an experiment that requires you to be in sunlight all the time. It doesn't matter, but mostly it's for power. So there is a way to obtain these orbits that face basically always at the sun. I'll do a sketch. By exploiting something that comes from nature, a perturbation that comes from nature that we usually don't like, but in this case we do, because it does have an effect on the big omega that we can exploit. So let's sketch a generic configuration for the planet, the satellite, and the sun. Say that this is the ECI fixed basis. Of course, we said that X is pointing at the Pisces constellation, is the line, the direction of the line of equinoxes, the vernal equinox. Then we said Z is the north direction of the planet, south north. The planet will be here. It actually has a certain size. We should really start thinking about the fact that this object has a size. And then Y completes the right-handed basis. And say that this particular position of the Earth on its orbit around the sun, and this is just an example, is, I don't know, the first day of the spring. So you are actually, with the x-axis, aligned with the direction of the vernal equinox. So this is the sun here, okay? And so in this particular time, direction Earth to sun and the x-axis are aligned. But this is just an example. It could be any other time, okay, just for simplicity. And my orbit is oriented, say that I am able to inject my satellite in such a way that the plane of the orbit, which we have represented in these x, y, z bases using three Euler angles, and then this has to do with the size and the shape, and this is where your dot is on that track, right? Say that I'm able to inject it in such a way that the plane ideally is in 90 degrees with the direction Earth-Sun. If that's the case, you can imagine how your satellite is always going to see the sun, right? The Earth is never going to be in the way. Do we see that? Sun is down there, this is my planet, and I just move around it so that the planet is never in the way. This way would be in the way if the sun is coming in that direction, right? So for some reason I'm able to do that, and then in practice means that I choose, in particular, a certain RAN, right, ascension of the ascending node. Remember, that's the line of nodes, such that I get exactly what I just said, that the orbit is, so this is the Earth, this is the north part of the orbit, this is the south part of the orbit below the equatorial plane, so that your satellite flies around the planet, different positions, but it doesn't matter what it really is. In this particular case, with this omega, if I wanted to really make it at 90 degrees, I would choose omega, exactly, 90, I would choose omega 90 degrees to be on the y-axis. But, it could be angled a little bit and still be able to see the sun all the time. So say that this is your condition. You have an omega such that you see the sun all the time. Now, this is fine for this particular time, right? The Earth is going around the sun. And some other time in the future, maybe, 3 months later, we are here. Now, the direction of the x, y, and z axes do not change. I decided that I don't want them to change. That's my quasi-inertial reference frame, so I hope I will make them parallel more or less, but they should be the same we have down there, so x, y, z. Now, if I stick to the model where there's nothing else, then pure Keplerian acceleration, the planet is a sphere, uniform mass distribution, well, then this is not going to change. So, again, the Earth has a certain size. And so the omega has remained whatever it was. Okay? And now I may be in trouble if I want to see the sun all the time. Maybe part of my orbit is actually behind the Earth, right? Do we see that? Is the sketch clear? If you don't change, so if in this configuration in spring you were able to see the sun all the time as you move on this line, which is the orbit, then you move to some other time, later time, and the Earth may be in the way to get sun in these portions of the orbit, maybe. That would be unfortunate if that's your goal, to get sun all the time. But this is there, and in fact, especially for low Earth orbits, so below few thousand kilometers, there is that J2 effect that, again, we're not going to formalize in any equations for now. So don't think you need to know any equations that have to do with J2 other than that function that I gave you at the very beginning, the rel acceleration with J2, just to show you what that effect does. But the fact that the planet is not exactly a sphere, that you take that sphere and you squeeze at the poles, has an effect on a bunch of these, and in particular on big omega. There is an equation that we'll see, among others, such that we can express the rate of change of omega as a function, in particular, of semi-major axis and inclination. And I'm not going to give you the expression because I want to be able to prove these differential equations later on. So the point now is just convincing you that orbital parameters are useful for this reason, as for many others. So there is actually a combination of appropriate, say, altitude, assume that, it's a circular orbit, so A is basically your radius, and inclination. There's not only one, but choosing an A, you get the right I, and vice versa, so that you can make the change, the rate of change of omega equal to, what do we call this? The angular velocity, the norm of the angular velocity of the Earth around the sun. Because the Earth has covered, the line that connects the Earth to the sun has covered a certain angle here, call it alpha ES, okay? And so if in this time here, for some reason I'm able somehow to make omega change of the same amount, then I continue to face the sun at all times. Do we see that? If I take the orbital plane and I move it and never change orientation, I'm not going to see the sun at some point, the Earth is in the way. But if I can rotate it, basically changing only big omega, at the same rate as this line that connects the sun and the Earth is rotating around, then I have what I want, which is a sun-synchronous orbit. So in other words, I get to this configuration, and instead of having this scenario here, I would have something. Let me try to redraw it here. This is the sun. This is my new position where I wasn't getting any sun. But now I have actually, this was my original big omega, omega at time 1. Actually, my omega has rotated and ended up here. And so now I am again in a situation where I see the sun at all times. So if that was somehow possible, I would be in great shape. I can see the sun at all times. It is possible by just exploiting the fact that the Earth is not flat. I'm sorry, it's not. No, it's not flat. We know that. It's not. It's not a sphere. Yeah, yeah. Some people still claim that. I've heard. You never know. So nature actually allows you to choose a combination of these two, so that if you start your orbit so that it's seeing the sun and is at the right combination of A and I, it will continue to see the sun because it's rotating at the same rate in the ECI. Is this clear what I'm doing here? You take this plane and you force it to rotate so that it's always looking at the sun. It's sun synchronous. So at this point, I'm really going to open MATLAB for the most part and show you how these would work. Let's see. Why is this off now? Now, this information is given in the chapter 4, which is what we're working on right now, orbital parameters. They give you the actual formula for that. At this point, there is no reason for me to do it. This is one of the 6 differential equations that we'll call Gauss variational equations that allow you to predict how the orbital parameters will change as you add more and more perturbations. You can have the J2 perturbation, you can have the drag force in low Earth orbit, you can have continuous thrust, you can have all sorts of things that are not included in this part. And they can go in these differential equations. So they give you the differential equation for the RAN. I don't really care about it now. I just care about the effect that the oblateness at the poles has on big omega. And give me a minute. Okay. So this always has some delay. Okay, finally. This is code that I'm not going to give to you because it's probably going to be homework too, for the most part. So you can film it and pause if you want, but I'm not gonna make it as easy as just giving it to you. Okay, let me comment out this. I was playing with this yesterday, so this is the fun part of the class where we do ISS later on when we talk about ground tracks. So I don't need this. This mouse is terrible. Okay, go away. Okay, so I'm going to show a few cases where I start my satellite. These are different orbital parameters for different types of orbits. So I have a sun-synchronous orbit, for example, that has this same major axis. Let's say that it's a circular one, so same major axis is radius. And I saved here the corresponding inclination that will give me sun-synchronous. So I'll just copy it here. And I don't really think I need to change the other ones. I don't really care about those. So what this function does, it does a lot of things. But for now, since I want to show that it's a sun-synchronous one, it will take orbital elements. It will convert it into state vector at that time. So that is orbital elements at initial time. I convert it into state vector, which I'm sure you've done because it was uncollected homework 3. So if you haven't, do it. So I convert that into R and V Cartesian coordinates in ECI. I take and integrate from those initial conditions for 1 day, in this case, the acceleration with J2. So I'm actually using this model where you would stop. We've seen this at the very beginning. You would stop at the part that is not highlighted if you had perfect Keplerian acceleration, but then all this ugliness here that we'll see at some point, is a more elaborate model that takes into account that shape, okay? And so I integrate it for one day, and then I plot a lot of things, but really the plot that I am going to pull up is, and look at, and hopefully works, is something like this. Yes?
Can you turn off the light on top of the projector so it's easier to see?
The light. Yes. This better? Okay, yeah. Is it coming okay on the camera? I don't think it makes any difference on the camera for some reason, but yeah, thank you. So say that this is time, and here I plot the, let's see, that angle, alpha of the Earth with respect to the Sun, and also the RAN. Regardless of the initial conditions here, what do you expect these two plots will look like? If I obtain a Sun-synchronous orbit, those two angles have to change with the same rate, right? Possibly you orient your initial orbit, as I said, so that it's looking entirely at the Sun, so you have the right initial orientation, and then the fact that it's changing with the same rate takes care of the rest. But regardless of the initial condition, they should be two parallel lines, right? Again, regardless of the initial conditions, they should change with the same rate. Make sense? Yes?
Sorry, for a Sunsynchronous orbit?
For a Sunsynchronous orbit, yes, yes, yes. So in other words, you want this angle big omega to change in time at the same speed, at the same rate as the angle between, the angle that is swept by the line that connects Sun and Earth. Clear? Yes?
So it's possible to be in orbit at such altitude that you're at a geostatic orbit. Is it possible to be so high that
Yeah,
you're always
absolutely. Yeah.
Is that an alternative to being in a...
Yeah. So you can be so high even if you're not in the right combination that is not making big omega rotate as that the Earth becomes a dot and you're so high that you always see the Sun. Absolutely.
You're always at the sort of closest point to the Sun. That's what I mean. So
Closest.
you would have to rotate slower than the Earth.
I'm not sure I understand the question.
Sorry, yeah.
No, that's fine.
Means you're always in between the Sun
And the Earth, exactly.
Oh, I see. So,
You're on the equatorial plane.
so you want to be in the equatorial plane.
I want to be so high that
I think the J2 effect. So we'll have to get there when we actually talk about the J2 and those differential equations you get. I think if you select that's the case. If you put yourself in an equatorial orbit, you completely lose the J2 effect because it's given by the squeezing at the poles. So that fact that you're squeezing at the poles is affecting the motion of your orbit if you have some inclination, but if you put yourself in the equatorial plane, it's not going to have any effect. So the differential equation that has to do with omega, the one equation that gives you omega dot, is such that this basically goes to zero. You don't do anything to it when you have zero inclination. So it's not going to rotate the plane. And remember, in an equatorial orbit, this actually kind of loses meaning.
right.
So,
Like I said, I'm not interested in changing
right.
and such. I'm just being in a position to altitude.
You can probably do that, but I wouldn't know. I should run some numbers. I wouldn't know what that altitude has to be. Probably pretty high.
Yeah, that's what I'm wondering when you could go outside your sphere.
Yeah, I'm not sure. I haven't run the calculation. No one does it, which probably means that
I think that's
it's too high. It's probably too high.
5 points around the Earth in a two-body system where...
Those are the Lagrangian points. Yeah. We don't. If I have time, we'll cover those. So there are some. There are some configurations. If you take into account now the attraction of the Sun and of the Earth on a satellite, so you study the two-body problem, there are some points that are equilibrium points where you kind of remain, you are actually orbiting the Earth, but from the point of view of Sun, Earth, and that satellite, you remain more or less in the same location. So that is kind of possible, but they are, that probably answers partially your question. If we have time, we'll cover those. I don't usually do it. They're called Lagrangian points. They are equilibrium positions when we do two-body problem, which I don't usually do in astrodynamics. But they are far, which means, again, they're expensive. But yeah, it is possible. Anything I want to say anything above LEO. I mean, getting to LEO is already pretty expensive in terms of how much fuel you need. You know, remember the space shuttle, how much of that was just tank and solid rocket boosters. The most of the mass was that. If you have to go even higher, you can imagine how much of the mass is fuel and you throw it away. So there's always a cost. So, any other questions? That was a good question, though. Reminded me that if I have time, I can do that stuff. Yeah. Okay, so yeah, I am integrating the acceleration that does have that effect. And then I just want to look at this plot for this case, and hopefully it will look like that. I have here the constant that tells me how quick the planet goes around the sun, somewhere down here. Just give me a second to find it. Don't tell me it crashed. It didn't plot anything? Okay. Did I pause?
I think you made an error in the inclination. You multiplied by pi over 180 twice.
That could be a problem. Where is it?
Line 19.
Oh, thank you. Yeah. That's not good. Stop. Yeah, I don't know what that is. It's probably creating some issues. Thank you. It's thinking. Okay, ignore this for now. Ignore this for now. We'll get there. Yeah, I mean, could probably run it for longer. Yeah, let's run it for a little longer. You don't see it very well there. That is the plot that I'm trying to reproduce where I have, where is my time? Time. There's never enough time. Here it is. Let's do 3 days. How about that? 3 days, you should see those two lines really being parallel to each other with some, inclination maybe. Yeah, you can probably see it, right? I can move the this thing here away. No, that's not what I wanted to do. Okay, well. Yeah. So the blue line is the behavior of big omega. So after I integrate the equations of motion, and I have the state vector in x, y, z, x dot, y dot, z dot, I do more. I take the Cartesian coordinates and I convert them back into orbital parameters in this function here. I just created a function where I can input x, y, z, x dot, y dot, z dot, and it outputs the 6 orbital parameters, which is still part of your uncollected homework 3. I just put it inside the function and I do it in a loop. So I can finally create re-extract the orbital parameters and show you that the RAN is actually changing at the same rate as the red line, which is the Earth's angular velocity around the sun. And I just wanted to show you where I do that. This is figure 2, right? Let me see, figure 1. Here it is. Yeah, very simple. The plot for the velocity of the Earth, I just took 2 pi divided by a year, whatever the number is. So that's, is it clear what's going on here? Why I picked that same major axis and why the corresponding inclination that I gave you, it's a secret for now, okay? You don't need to dig into that. There is an equation. But my point in showing you this is hopefully to justify why people are talking about orbital parameters. Can you imagine doing this in Cartesian coordinates? All the reasoning we went through, I want to orient the plane so that it's looking at the sign all the time. Yeah, you can do it in Cartesian coordinates. It would be a nightmare to do so. And again, we have equations, differential equations for these 6 that tell us exactly how we can affect them, which for the most part is a negative effect. In some cases, it's a good thing. Now, another example that I have, real quick, which I think we discussed at some point, was these Molniya orbits, remember? Let me first talk about ground tracks. I don't want to do that now. Yeah, let's do that first. I think I just need this board. Okay, what are ground tracks? There isn't really too much to say. A couple things. Okay, so planet, center of the planet, x-axis of the ECI, y-axis of the ECI, z-axis, the satellite is somewhere at a certain time. This is your spacecraft. There is obviously always, you can imagine always a point that is the intersection between that position vector and the surface of the planet. Okay? So, since this is a sphere, we said this several times, angles are a good way to locate objects. So, I could call this, which is a right ascension, I could call this the longitude, right, of my satellite. This angle here between x and the projection of r on the xy plane, and this other angle between, which is basically the angle with the equatorial plane, called that latitude. Okay? Except what? And so, and as the satellite goes around on its orbit, whatever it does, this point will describe some path on the planet, on the surface of the planet, and that's what I call ground track of that spacecraft. Now, what am I missing here? Remember, we are sitting here on this planet. We want to know where the satellite is with respect to us. Is that a good way of operating? Is that something that I completely forgot about reality here? Nope? Yes? What happens to the planet? What is the planet doing all the time? It's spinning. So we don't really, you probably know what longitude and latitude are, but the satellite is, the planet is rotating. So this is omega of the Earth with respect to the inertial observer. So I don't think I can call this the longitude. I probably don't want to call that the longitude, because as we know, that's counted from the meridian of Greenwich, right? That's what we usually do. So there is probably some correction I have to make wherever that line is, Greenwich line, at any given time. This is not the longitude. So if this is the line of Greenwich in the UK, it's a nice place. There's a very nice observatory there. They also show you all the different units that the British use that make no sense to me, but they're there. They have all samples that show you how much a yard is and other stuff that I never heard of, but it's a nice place. So if this is the meridian of Greenwich, this is the zero for us. We start counting longitudes from here, so this is the longitude, right? Agree? Of the spacecraft. But this thing here is moving. So at any given time, you can project r on the plane and compute the angle with the x-axis, but you need a way to continuously correct for the alpha of Greenwich. You need to subtract this, right? We following? If you want to have longitudinal, I haven't talked really about ground tracks yet because they're not done on the sphere. But if I want to compute those two angles, and say that you have your vector xi plus yj plus zk, it should be pretty easy to compute these two, an arctangent, an arccosine, whatever you need to do. So you can compute right away from these coordinates here. You can figure out immediately the latitude, and I don't know what I want to call these. Longitude prime is not the real longitude, right? So I can compute that right away. But then I need to have the current position of the planet. I need to know where Greenwich is. How much has the Earth rotated with respect to the x direction? So we'll see how that is done. There are functions that I actually posted them on Canvas that give you, given a certain date, you can compute this angle. It's just given. It's a function that allows you to input a date and extract the alpha Greenwich. Now, the other thing that is not usually done, though, is we don't talk about ground tracks on the sphere. We take the map of the planet, we put it in a rectangle, which is an abuse, but that's what we do. So I'm not even going to try to reproduce the continents here. I don't want to do that. Maybe I can try. Say that this is the UK up here somehow. This is UK. France, right? Spain down here. This is my home in Italy, etc., etc. Right? So Greenwich will be somewhere here, right? So these are called Mercator planes. I'm sorry, Mercator maps. This is the last name of, I think, a British gentleman who invented this. What we do here, we say, okay, this is the equator, it's 0, you have the latitude on the y-axis, 0 usually, minus 90 degrees, and plus 90 degrees. And then here, unfortunately, I put Greenwich here, but I would say that usually people do it different ways. The way I do it here in this code, I actually have 0 here, so Greenwich will actually be here, 0 to 360. But it doesn't matter. You can have 0 here, plus 180, minus 180. It's the same story. There are different versions. So if Greenwich is there, then I guess the UK will be actually here, right? And France here, etc., etc. Okay. I don't know if you can see Italy from there, because Italy is 1 hour, Rome is 1 hour ahead. So yeah, you should be able to, right? Yeah, it'll be down here. I can't do maps. Anyways, so with these, and so the satellite will change if you correct for the longitude, taking into account the fact that you have to subtract these at all times, whatever that is. You obtain longitude and latitude, and the ground track of a satellite is the trace of longitude and latitude, whatever that is, on this kind of map, which is a 2D representation. There is no altitude information here. But still, it's a very good piece of information, because if you are somewhere on the planet at a certain longitude and latitude, you know more or less when the satellite will be the closest, and you can probably talk to it with your ground station, or you can see it, like in the case of the ISS, when it's so big and so low and bright if it's at night. So is this clear? You extract, so how do you do ground tracks? If you have a position in Cartesian coordinates r, you don't even talk about velocity here, extract these two angles with the x-axis and with the equatorial plane, and then you have to subtract for alpha of Greenwich, which is the two functions I gave you. So this is exactly what this code is doing. So you have these two functions, they're called Julian date and GST time. Okay, this function does the following. You input a certain date, year, month, the day of that month, and then time, and that is Greenwich time, GMT time, okay? So that means noon, the way I have it right there. And that function, you run it, it will generate a incredibly big number, which is how many days have passed since I don't know what day in the past, even before the birth of Christ, or I have no idea. But it's a Julian date. So it's basically there is a 0 set at some point, and this number just keeps increasing all the time. And that's called Julian date. Now the next function, this is literature, this is provided functions to everybody. The GST time takes the Julian date as an input, that's the only thing that it can take, and is giving you in radians this guy here. They're given. You can find them probably anywhere online. Okay, so now I do have that piece of information, at least at initial time, where Greenwich is. And then you can imagine, knowing the angular velocity of the Earth around this spin axis, you can keep adding to this initial Greenwich angle, right? As long as you know what it is at initial time, which is exactly this omega e that I have right here. This is the Earth's angular velocity about the spin axis. It's a known constant. Okay, so now what I'm going to show you is an example. So I extract the angles at the bottom here after I do my integration in Cartesian coordinates. I go here, where I convert into orbital parameters. I have these additional instructions where I extract the latitude, which is an arc sine of the z, if you have the position vector in Cartesian coordinates, divided by the norm of the vector position. Simple trigonometry. And the longitude, but this is not corrected longitude for now. So the longitude is the angle with the x direction of the ECI. I have to correct it, which I do later. It's an arctangent of this is the y component divided by the z component. The x component, as you can imagine. Again, simple trigonometry. So I just extract for each position that I'm given after I integrated the equation of motion, the latitude, which by the way, I don't have to correct, right? You don't have to correct the latitude. The fact that the planet is spinning, it doesn't require any correction. And the longitude. Okay. Now, this is for the RAN. We don't care anymore. Now, this is the instruction where I go and correct the longitude. I take whatever I computed before, that I call ln, and subtract the GST, which is the initial angle for Greenwich, plus, here I'm taking into account how much time has gone by since the initial condition. I'm doing this in one instruction, but this is a vector. The longitude is a vector of longitudes for the entire orbit. So the corrected longitude will be a vector of longitudes for the entire orbit. And GST plus the omega of the Earth T out is taking into account the position of Greenwich at each time step. And I do a mod over 2 pi so that it remains inside the 0 to pi range, which is what I said for the Mercator plane right there. And so that's all. And then I plot it into that kind of plot, minus 90, plus 90, 0 to 360. So I have a few examples that are the very basic ones. If I take a geostationary orbit, do you remember what a geostationary orbit is? In the equatorial plane, at a certain altitude, which is about 42,000 kilometers, well, that's the altitude, 35,000 plus kilometers, radius is 42,000, circular, so that you are rotating at the same rate of the planet and you are above a certain location, right? So I don't even know what the location is right now, I think. I just selected the right inclination. Inclination is 0 as well, sorry. 0 inclination, 0 eccentricity, same major axis is the right one. So if I run these, now I can look at at the other plots that I ignored before. Okay, first of all, the big omega, this is to respond to the comment of your colleague had before when I said that nothing is going to happen to the RAN. The J2 effect is lost if you are in the equatorial plane. Okay, forget about all these points that we have around here. The red one, and so this is the ground track of that satellite. Here it is, down here. See, it starts here and ends here and changes very little because it's just a stationary satellite. That's what you want. So I just randomly selected the other orbital parameters, so it seems like it's looking down at whatever is a longitude 35 degrees. By the way, it's 35 east, of course. If we start at Greenwich, anything is east from there, 0 to 360. So that makes sense, right? It's oscillating a little bit because there is J2 has an effect even at those altitudes a little bit, but it's not something you can really appreciate. It changes on maybe the second digit, first digit. So it's definitely pointing down always at the same spot on the planet, which makes sense. Geostationary orbit, right? Now, if I change it to, I better speed up. If I change it to, let's do the ISS, okay? You can do the Molniya. You have the data here. You can figure it out, find it on the book. The Molniya will show you at ground track where, let's do it. You know what? Let's do it. I have time. I think I have time. I always think I have time. So this is Molniya semi-major axis. These are, remember, the Russians that don't have the luxury to go into geostationary type of orbits. They have higher inclinations. So they try to create a condition where they spend a lot of time at the apogee of the highly eccentric orbit that they can create over a certain location on the planet. So this should give me, oh my goodness, no. How? Okay, I don't know what happened. I don't want to know. Okay, do it again. So these are semi-major axis and inclination to obtain a Molniya orbit, and it's not running. Oh, it's running. Okay. Okay, so by the way, that blue dot there is Gainesville. I just googled the longitude and latitude. So I didn't select anything with particular intelligence here. The point that I wanted to make is imagine that you want to spy a location at this longitude. That is actually the apogee of your orbit. You're spending, so you're going up. Again, this is projected on the Mercator plane. But you're going up there, stay there for a while. So it's going to take a while to run this portion of the orbit because it's the apogee part of the orbit, which is exactly what you want for Molniya orbits. So when you see orbits like this, it means there is something interesting, probably at this longitude or maybe at this other one, which is, and this is how it looks in 3D, highly eccentric orbit, and you're spending a lot of time up here, hopefully at an altitude where you're moving with the planet. You're rotating at the same rate of the planet, more or less, so that you can spy that spot as much as possible. But now, the very interesting part is ISS in Gainesville, right? So, if you go on this website right here, is a NASA website where you can download all sorts of information about the ISS. They give you certain times the orbital parameters and or Cartesian coordinates. They give you information about the maneuvers, etc. So at this particular time, which was, so this is how it's provided on their website. Year 2017, day 46 from the beginning of the year, which was Valentine's Day, yesterday. Because January is 31 days. No, it's actually 2 days. 31, 15, yeah, it's today. Yeah, okay. So, sorry, it's today at noon GMT. That's the time in London, which means 7 a.m. for us, 5 hours, right? So 5 hours, 7 a.m. this morning, the ISS had these orbital parameters that I downloaded. And so my app told me that at 8 p.m. there should be a point where I can see the ISS, and hopefully this works. Oh, I'm running for 3 days. I don't need to run. I'm sorry, let me stop this. This is too long. I want to do 1 day only. Let me do it again, because it's just tonight. So, okay, 1 day. Sorry about that. Okay, forget about this. Okay, so this is now something interesting. This is my ground track. It starts right there. It goes around a few times. It ends somewhere here for 1 day. Gainesville is the blue dot, and that's the closest I get to Gainesville. How do I compute that? I just subtract the vector of longitude and latitudes, subtract the Gainesville longitude and latitude, and see what is the minimum. Simple mean instruction in MATLAB. And I locate when in the time vector of positions and velocities that happens. And it's telling me that it's happening in hours. This is in hours. 13 hours, 0.06 after the initial condition, which was, again, 7 a.m. for us. So 13 hours later is 8 p.m. So I'm doing this in MATLAB. And it's very approximate because I am not taking into account something important. Maybe in a day is not that important, but J2 is there. What is it that is affecting the International Space Station that I am not modeling right now in my drag? Drag is not there. That object is pretty big. So drag is definitely not in the picture. So maybe predicting to see the ISS with this program, too many days into the future is not a good idea. But for a day, it's working pretty well. And this is all done by simple trigonometry, taking an arcsine and an arctangent of the position based on the x, y, z coordinates of this position vector, subtracting these, which is really just given to you. You just have to use those Julian date and GST functions that I gave you. They are on Canvas. So last year, homework 2, and I think I'll do something similar, was really based on ground tracks for ISS. Which I think is very entertaining. I found it amazing that I could forecast this. I did last year. Yesterday I played. I said, I hope it works this year as well, and it did work, of course, but you never know. So this is consistent. I haven't tried it for more than 1 or 2 days. Again, it will lose accuracy. But try to reproduce this. Try to create the ground track for the ISS. Go on their website. Just search for ISS orbital parameters and try to do this yourself. It's all based really on uncollected homework 3. Orbital parameters to Cartesian coordinates and vice versa. And the additional piece of code that you really need to use is these 2 functions that I have at the very top. I think there's really nothing else that I want to say other than, do you have any questions? You can do this in SDK. Those of you who have started playing with SDK, you can verify that this matches what you get in SDK, which is also another good exercise.